Energy is covered in 2 chapters of this book, and we're going to be jumping back and forth a little bit. We're going to start, however, with the concept of work. You'll see that as we begin talking about energy, we're going to talk a lot about the concepts of energy. These concepts are very important from a definitional kind of standpoint, defining how we talk about energy and related concepts like work. Eventually, we'll move into the really meaty kinds of example problems. Work is a concept that is the energy expended by a force on a system, or you can also think about it as the energy given to a system by an external force. To look at work, you can look at all the forces at once, or you can look at one force at a time. You can see how much energy is added to a system or expended by a force on a system, just one force at a time, or you can look at a bunch of different forces. The equation for work is shown here. Work is equal to force dot a displacement. That dot signifies a dot product, which is a kind of multiplying vectors. You see that the force is a vector, force has always been a vector, and this is displacement, which is also a vector. If you're multiplying 2 vectors, you have to choose how you're going to multiply them. And the way that it mathematically works out in this case is that we choose something called a dot product. A dot product is the first thing. So the first thing here is the force. The second thing here is the displacement. And so when you multiply 2 vectors with a dot product, you take the magnitude of the first thing. So, just let's say the force is the force of gravity, because you can definitely include the force of gravity being applied here. We'll talk about the subtleties with that. You can include the force of gravity as work, but we end up changing it around later on. Anyway, you can take the force of gravity. Let's say that that's 19 newtons down. Well, the magnitude of that is just going to be 19 newtons. So you plug in 19 newtons in for the force right there. You ignore the direction. Then let's say the object falls by 4 meters down, because objects fall down. Well, that displacement would be 4 meters, and we'd ignore the down from now. And then we'd say, oh, cosine theta. Cosine theta, that theta right there, that angle, you can see here, is the angle between the direction of the force and the direction of motion. If we have an object falling down because of gravity, then what we do is we say, the direction of the gravity is down. Gravity is pulling something down. And then we say, okay, what is the direction that it's actually moving? Well, it's also moving down. And so what is the angle between down and down? That angle is 0 degrees. So what is the cosine of 0 degrees? Well, it's 1. Cosine of 0 is 1. You've got an angle like that, just perfectly horizontal. That's a cosine of 1 right there. And so in that kind of case, the cosine of theta is just 1, and we can kind of, well, we're multiplying it by 1. We're kind of ignoring it. There are other cases where you might have an object like this, and you're not pushing straight down on it. You're not pushing straight forward on it. You might be pushing at an angle. We'll talk about cases like that where you're pushing at an angle, and then you do have a theta that you need to include there, because an object might be moving in that direction. I'm pushing it in that direction, or it is moving in that direction. Its displacement is in that direction, but I am pushing it. The force that I'm applying is in a slightly different direction. The displacement is that way. The direction of the direction of the force is that way, and then you would have a theta that you need to pay attention to. If you push at an angle, that's not very efficient. Like imagine pushing at a really, really vertical kind of angle like that, that doesn't move things around very quick. Pushing like that is the most efficient. And so pushing at an intermediate angle would have an intermediate efficiency. And that's what the work is measuring in a way. Let's do an example. Let's do several examples, in fact. The work is equal to the force times the displacement times the cosine of theta. That is the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. And you are pushing a box across the floor. Put the following cases in order from the most amount of work to the least amount of work. There are 4 cases here. This is an example problem for you to be able to do in your own time. We start with a 30 Newton force pushing in the direction of motion for 10 meters. Now, on a problem like this, identifying that 30 newtons is the magnitude of your force and 10 meters is the magnitude of your displacement, that's pretty easy, frankly. We can just read the problem. We're like, okay, yeah, the force is 30 newtons, the displacement is 10 meters. The much more challenging part is figuring out the angle to plug in. We are pushing in the direction of motion. If the direction of motion is to the left, then the force is to the left, because that's where we're pushing. And so what is the angle between the left force and the left direction of motion? And that's 0, yeah. And so we plug in 0 for cosine of theta, and we get 1 again. I say it's much more difficult, but you see that it's from like 0 difficulty to 0.1 difficulty. And so it's not that big of a deal, I think. The next one, a 25 Newton push at an angle of 60 degrees from the direction of motion for 5 meters. Well, okay, 25 newtons, that's our force. 5 meters, that's our displacement. 60 degrees from the direction of motion. Well, it says it right there. We are 60 degrees off from the direction of motion, and so we plug in cosine of 60. And cosine of 60 is less than 1. Cosine of 60, let's see, is 1/2, in fact. And so you're only getting half the work out of it that you could be. If you pushed directly on, you'd get a certain amount of work. But if you're pushing at an angle of 60 degrees, then cosine of 60 is 1/2. And the force that you're getting out of that, the work that you're getting out of that is artificially reduced because you're really not pushing in the right direction. What about 10 newtons of friction for 6 meters? Now this is where it gets more interesting. 10 newtons, okay, that's the force. 6 meters, okay, that's the displacement. But what is the angle between the direction of the friction and the direction of the motion? Yeah, 180 degrees. So if you are pushing something across an object like that, and the push is therefore that way, and the direction of the friction is that way, well, the angle between the force and the friction is 180 degrees. What is the cosine of 180? Well, it's -1. Work is the energy added to a system by a force. Friction is not known for adding energy to things. You usually don't have friction giving something else energy. Usually you have friction slowing things down. If friction is slowing things down, then it's removing energy from something. And so the work done by friction is almost always a negative number. That's not always true, and we'll actually look at car engines in not too long and see how the friction with the road actually gives an object energy as it pushes itself along the road using the friction. A car's tires will stay on the road with friction. The friction is what keeps them from spinning out. And so it's that friction that allows themselves to move the car forward like that. And so that's one place where friction actually does have a positive amount of work. But in everything else, friction is going to have a negative amount of work because it slows things down and it removes energy from a system. So that means a negative amount of work. One comment that I want to make on the word work in this case, you have already noticed that physics terms don't always line up with the terms that we use in our everyday lives. When we talk about forces and velocities and accelerations, what we mean when we're just talking to each other casually is not always the way that that word is used in physics terms. And that's okay. It's okay to have one definition for one case and another definition for another case. That's just how language works. Using physics, we talk about work in terms of things like energy. We're all used to the concept of work like, well, I'm working right now because I'm teaching you. But physics, it's a different kind of work that we're using in this kind of case. It is the energy flow into a system. The work done on the system is the energy that's flowing into that system. The last example on here is 25 newtons of normal force. Ooh, okay. Well, 25 newtons of normal force, that points up, and the force is 25 newtons. And what's the displacement from 25 newtons of normal force? Yeah, 0. Yeah, if it's just normal force, if you've just got an object sitting on another object, you've got no movement. And so if you've got no movement, your displacement is 0. And if your displacement is 0, the work is 0. This is something that has bothered a lot of people, that you can have an object exerting a force forever. I can leave this toy car on my calculator forever, and the calculator is always exerting a force on the car. It will never stop. For 1 billion years, the calculator will exert a force on the car. But it doesn't use up anything. It doesn't use up any energy or anything like that. And that's because there's no motion. You only get a change in energy when you have motion. And so therefore, things just sitting there, if the force is just the normal force, nobody cares. It's not changing the energy at all. You might have normal force pushing up on something and gravity pulling down on something. If you've got gravity pulling down, well, if something is falling like that, something's falling, then you do have a change in energy. But if something is just resting there, okay, gravity's acting on it, normal force is acting on it, but it's not moving, and so there's no energy being changed in that object. That has bothered many people, including me. That's one of the things that bothered me when I was younger. Like, why doesn't every force expend energy? And it's because things aren't moving. If nothing's moving, no energy is being expended. When I talk about the misconceptions that students have had in the past, half the time I'm talking about myself when I was learning this stuff. And I figure that if I had these misconceptions, then you might as well, and I might as well address them. We can actually calculate out all these answers here, but it's exactly what you'd expect. 30 newtons times 10 meters times the cosine of 0 is 300 joules because it's just 30 times 10. 25 newtons times 5 meters times 1/2 because of cosine is 60, 62.5 joules. 10 newtons of friction for 6 meters, well, that's 10 times 6, which is 60. But because friction acts opposite the direction of motion and the cosine of 180 is -1, then you get -60 instead of +60. And then 25 newtons of normal force is 0 joules. This brings us to work and its relationship with kinetic energy. There are actually 2 different kinds of kinetic energy that we will learn about. And the first type of kinetic energy is the main one, and it's called linear kinetic or translational kinetic energy. Or more commonly, it's just called kinetic energy. The book will sometimes call it kinetic energy, and it will sometimes call it translational kinetic energy. And you have to be very careful of how it's discussing things. The alternative is rotational kinetic energy. And so I'll try to clue you in on when the book is talking about one thing or another thing. But this is the energy from an object just going in a straight line. If you've got an object just moving somewhere, then it's got kinetic energy. Kinetic just means things that are moving. The equation for kinetic energy, Ke, that stands for kinetic energy, is equal to 1/2 times the mass of the object times the velocity squared. Interestingly, if you take the dot product of two of the same vectors, if you take two vectors like velocity that are pointed in the same direction, like if you take the same velocity twice, let's say an object is moving at 4 meters per second north, then in the kinetic energy equation, you'd have 4 meters per second north times 4 meters per second north. If that's a dot product in there, then 4 meters per second north, well, you take the 4 meters per second, that's your amount, and you save the direction for later, and you take the other 4 meters per second, and you save the direction for later, and so you get 16 meters squared per second squared, and then you have to find the angle between north, and that's 0, and so the cosine of 0 is 1, and so you end up getting the velocity squared using the dot product is just the magnitude of the velocity squared. So if you have 4 meters per second, then v squared is just 16 meters squared per second squared. Notice what happened with the units there, that if it's meters per second, but I'm squaring it, then it's meters squared per second squared. Anyway, the point of that is that you don't need to do anything special when you plug a vector in for like velocity here. You don't need to do anything weird with the fact that it's a vector. You just take the magnitude and you square it. And so the direction of the velocity does not matter for kinetic energy. If you've got two objects, and one is going this way, and the other one is going this way, and they're going at the same speed as each other, and they have the same mass, then they have the exact same kinetic energy. It does not matter which direction they're going. If they're going at the same speed and they have the same mass, then their kinetic energies will be the same. You do not need to specify directions for kinetic energy. That's nice. For a little while, for not very long at all, we're going to be able to get away from all the trigonometry that we've been doing. We still have a little bit of trig that we need to do, but just a lot less trig now. And I think that most people are okay with that. The units of all this is joules. This is true of all energy. 1 joule is equal to 1 kilogram meters squared per second squared. You can totally rederive this on your own. Look at the equation for kinetic energy. 1/2 does not have any units to it. 1/2 is just a fraction, it's just a number. Mass, though, that definitely has units. The units of mass is kilograms. And so you come down here and you see kilograms for the units of energy. And then velocity, well, that's meters per second. But it's velocity squared, so therefore it's not meters per second, it's meters squared per second squared. And so the units of energy is kilograms meters squared per second squared. But nobody wants to write that down every single time. That's a lot to write down whenever you're writing down the units of energy. And it's a lot to say, it's even more to say. And so for historical reasons, we decided to just call the units of energy joules. 1 joule or many joules, whatever. That is the unit of energy. Just like how newtons are very similar. 1 newton is 1 kilogram meter per second squared. And that's for forces, and we figured that out because F equals ma. And so we're like, nobody wants to write down kilograms meters per second squared every time, so let's just call it a newton instead. Same thing for joules. It's because physicists are lazy that we give them these extra names. Interestingly, the units of work are also joules. If you look at what a force is a Newton. And a Newton, we said, is a kilogram meter per second squared. Remember, force is equal to ma, F equals ma, and the unit of mass is kilograms, and the unit of A, acceleration, is meters per second squared. And so the units for force is kilograms meters per second squared. And then we multiply it by a distance. Distance is in meters. And so then we've got a Newton times a meter. Well, a Newton is a kilogram meters per second squared, and times a meter. That gets you kilograms meters squared per second squared, because you had an extra thing of meters in there. But that's the exact same units as a joule. So work is measured in joules, and energy is measured in joules. They are the same sort of thing. And so that means that we're going to be able to set them equal to each other eventually. An example of kinetic energy. We have a 75 kilogram person walking at 2 meters per second. Compare the kinetic energy of that person to the same person running at 4 meters per second instead of 2. The only thing we're changing is the speed. What we do is we say kinetic energy is equal to 1/2 times the mass, 75, times the velocity. Well, we're doing this twice because we want to compare. So the first time we plug in 2, and we find the kinetic energy of the person that's walking, and we get a number, and that number ends up being 150 joules, by the way. If you've got 1/2 times 75 times 2 squared, then that's 1/2 times 75 times 4, or 75 times 2, and that's 150 joules. Compare that to someone that's running at 4 meters per second. Well, you plug in 4 there, you get 16, 1/2 times 16 times 75, that's 600 joules. The person walking has 150 joules of energy. The person running has 600 joules of energy. The person doubled their speed, but increased their kinetic energy by a factor of 4. Kinetic energy is not linear. If you double something's speed or double its velocity, its kinetic energy increases by a factor of 4. If you increase something's speed by a factor of 10, you increase the kinetic energy by a factor of 100. That's actually one reason asteroids, of all things, are so dangerous, because they're coming in at maybe 20 kilometers per second, which is an absolutely astounding velocity. And they're already very heavy, so their mass is large, but their velocity is what makes an incoming asteroid so dangerous, because their velocity is so ridiculously huge. And then you square that, and you get an even more ridiculous amount of energy being deposited on the surface of the Earth in a gigantic explosion. Anyway, I'm an astrophysicist, so I like talking about that stuff. But yeah, always keep in mind, doubling the velocity of something will increase its kinetic energy by a factor of 4. Alternatively, if you increase the kinetic energy of something by a factor of 4, you merely double its velocity. It works both ways. Let's continue on with the WorkEnergy Theorem. There are reasons that I don't really like teaching this, but it ends up being very important the way that the book talks about things. The reason that I don't like teaching this is that at one of my previous universities, and I will not say which, there were about 10 of us physicists that were all in a room discussing how we were going to teach a certain thing. We were all teaching out of the same book, and we had a test that we gave all of our students. Every professor gave their students the exact same test, and so we had to be on the same page for a lot of things. And we were discussing how to talk about the WorkEnergy Theorem. And the 10 professors ended up spending the next 2 hours debating the actual meaning of the WorkEnergy Theorem. after 2 hours, we could not come to a conclusion. We could not come to a consensus on what the work-energy theorem really means. 10 PhDs together in a room could not agree. And I just sat there not speaking because I was having too much fun just watching people argue about something that doesn't even matter, because that's my personality type. And so someone definitely needs to redefine this in a way that everyone can understand. And so I'm going to try my best to define it in a useful way, in a way that is both simple and useful. And I hope it works. And we'll see. The work-energy theorem says that the total amount of work done on an object is equal to the change in kinetic energy of that object. So work total. Take the work from every single force on an object, add them all up. That equals the change in kinetic energy of that object. Now, this is actually pretty quick when you're thinking about simple cases. Let's go back to the case of the normal force acting on something. This object rolls too well. There, I took off the wheels. Let's look at this object. Well, what are the forces on the car? We've got the normal force pointed up on it, preventing it from falling through the calculator. We've got the gravitational force trying to make it fall through the calculator. Well, we could calculate the amount of work done by the normal force. Oh wait, that's 0 because it's not moving. And then we calculate the amount of work done by gravity on this object. Oh, it's also 0 because it's not moving. And so the total work done on that car is 0. And let's see, the work total is equal to the change in kinetic energy. Is the kinetic energy changing? Oh, it looks like it isn't because it's not speeding up or slowing down. Kinetic energy will only change if it's speeding up or slowing down. If its velocity is changing, then the kinetic energy will change. I could actually just have it moving at a constant rate like that, and that's totally fine because the kinetic energy is constant. And so there's no change in kinetic energy as something moves around. In either case, there's no change in kinetic energy. And therefore, there's no work being done. So in cases like that, the work-energy theorem makes total sense. And everything is working just fine. Question, so it isn't only valid when something changes, so not resting at constant speed. It should be valid all the time. There should never be a case where the work-energy theorem is not valid. Actually, I said that and I immediately thought, okay, it does get weird in relativity and quantum mechanics, but now that I think about it, I think it actually still holds in relativity and quantum mechanics because we like define around it. So in this class, it's always going to be true. However, in this class, it's not always going to be useful. There are many things in this world that are true but not useful. And we will take the work-energy theorem, and eventually we're going to mold it into something that is both true and useful. Right now, the work-energy theorem is true but not useful. But eventually, it will be. We will create something that is both true and useful out of it. We need to remember also that delta represents final minus initial. Whenever we see delta in an equation, we can always think final whatever minus initial whatever. We look at delta KE, change in kinetic energy. That is going to be the final kinetic energy, whatever kinetic energy you have at the end of the problem, minus whatever kinetic energy you had at the beginning of the problem, final minus initial. The work, as I said, can come from many different forces. We've got gravity, we've got springs, we've got normal, we've got someone pushing on something, we've got all sorts of stuff. Next semester, you will add to our list from this semester things like electric force and magnetic force and you'll see all sorts of interesting things that can happen with those forces. You'll see even more different forces in your engineering classes. There's lots of different things you can do with work, with the forces that are considered in work. And just a reminder for you that kinetic energy does take two forms. It can be linear kinetic, or otherwise known as translational kinetic, just the energy of going forward, or it can be rotational kinetic, which we will talk about in a couple weeks. Right now, we're just going to be talking about regular linear kinetic. I took all the examples that we did before. You're pushing a box across the floor, 30 Newton push in the direction of motion for 10 meters. Well, that's 300 joules. What is the, or assume that the box is 8 kilograms and it starts at rest. What is the final velocity in each case? So I give you all the numbers that you should be looking out for. So first of all, okay, we've got a 30 Newton push on an 8 kilogram box in the direction of motion. We already established that that ended up being 300 joules of work. So if you've got 300 joules of work on something, and that something is 8 kilograms and it starts at rest, you can find the final velocity of that. You can also find that if you've got 25 newtons of push at an angle of 60 degrees from the direction of motion for 5 meters. Well, that's 62.5 joules. You can use that to figure out, okay, it starts at rest, its mass is 8 kilograms, what's its final velocity? That's much more difficult with the friction, because if you're starting off at rest, then you're not really moving, right? If you start off at rest, then you're not going to be moving 6 meters. So this third one doesn't actually mean anything when you're starting at rest. So that's why I crossed it out. And then 25 newtons of normal force, well, we already discussed that's going to be 0 joules because there's 0 change in motion. So to show my work, we've got an 8 kilogram object starting at rest. We know that the work on that object is equal to the change in kinetic energy. If we take just the first example, I'm just going to show you the first example with the 300 joules. It's simple enough to figure out the rest from there. 300 joules is equal to change in kinetic energy. Well, change in kinetic energy is going to be the kinetic energy final minus the kinetic energy initial. But we said that it starts from rest. And if it starts from rest, then the initial velocity is 0. 1/2 times the mass times the velocity is 0 squared. Well, that's going to be 0. So the kinetic energy of an object at rest is 0, and it was initially at rest. So we've got a 0 there. So then we have 300 is equal to 1/2 times the mass times the final velocity squared. We can plug in the mass, 8 kilograms, and then we've only got one unknown. And so we find that V final is equal to 8.66 meters per second. I'll give you all the answers to this on this slide. We see that with this same object, it's 8.66 meters per second as the final velocity. If you add 300 joules, 3.95 meters per second if you add 62.5 joules. And the friction doesn't really make any sense in this case. And the normal force doesn't change the velocity at all. Alternatively, we could do this exact same problem where the box is still 8 kilograms, but it starts off at an initial velocity of 5 meters per second. It does not start off at rest, it starts off at 5 meters per second. What is the final velocity in each of these cases? I have that all prepared here. The work is equal to the change in kinetic energy. 300 is the work that we did in the very first example. That's equal to the kinetic energy final minus the kinetic energy initial. Kinetic energy initial is not 0 because in this case, we start at 5 meters per second. And so if you're in motion, you have kinetic energy. 300 is equal to 1/2 times the mass times the final velocity squared minus 1/2 times the mass times the initial velocity squared. If you're happy with doing algebra, then you can You can factor out the 1/2 and the m out of that if you want. Usually I don't see a need to do that. You can plug in what you know. 300 is equal to 1/2 times 8 times v final squared minus 1/2 times 8 times 5 squared. And you find that the final velocity is going to equal 10 meters per second. Interesting to note here that even though the initial velocity was increased by 5 meters per second, we went from initial velocity of 0 to initial velocity of 5 meters per second difference between the initial velocities. Despite that, the final velocities did not change by 5 meters per second. Going from 8.66 meters per second to 10 meters per second is not a change of 5 meters per second. And so the final velocity increases by less than it did in the other example. This goes back to how nonlinear kinetic energy is. If you've got an object that you double the amount of kinetic energy, well, that does not double the speed. If you increase the kinetic energy by a factor of 4, well, then that doubles the speed. And so we see that similar kind of feature played out here. Now it's time to talk about gravitational work. Gravity is one of the many forces that can cause a work, because any force can cause work. Just so happens that gravity is going to be one of the more common kinds of forces that could do work on a system. So we take our WorkEnergy theorem, work total is equal to change in kinetic energy. But work total, well, the total work is just going to be the work from one force plus the work from another force plus the work from another force plus the work from another force. And that'll make the total work, and that'll equal the change in kinetic energy. So let's break up the total work into the work done by gravity, plus the work done by springs, plus the work done by other things, I don't know yet. And that's equal to the change in kinetic energy. We can start pulling things out of the work total and start saying, okay, I'm going to just find the work due to one thing at a time. And the first thing we're going to do that with is the work done by gravity. So let's figure out what the work done by gravity actually is. The work done by gravity, well, it should be fairly clear that the work done by gravity is going to be from pulling things down. So let's assume that something is just falling straight down. If something is falling straight down, well, the force of gravity on it is going to be m times g in the negative direction. The work is going to be the force of gravity times the distance that it falls times the cosine of the angle between them. And here we're just assuming something is falling straight down, nothing weird. So the force of gravity, the direction is down. The displacement is down because it's falling down. Therefore, the cosine of the angle is 1. And so we have that the work done by gravity is equal to the force times the displacement times cosine of theta is equal to 1. So it's just force times displacement. But the force is equal to mg. And we've got the displacement. So the work done by gravity is m times g times the height through which it fell, mgd. Sometimes you may have seen this as mgy or mgh or some variant on that, but it's always the mass times the acceleration due to gravity times some letter that is referring to how far up or down it went. In this case, it went down. We can do the same thing for work from gravity going up, and now assume that you're lifting something up. Well, that's going to be another force. You actually pushing something up is a different force, but we're just looking from the work from gravity. We don't care about any other kinds of work. We are just looking at the work from gravity. Now the force of gravity is down, but the displacement, the distance that it's going, is up. Therefore, the cosine of theta, because you've got gravity down, distance up, the angle between down and up is 180 degrees. Cosine of 180 is -1. you see that if you are lifting something up, gravity is doing negative work on that object. Which, yeah, already this is getting weird and confusing, but I'm going to tie it up together to be more clear. We see that as an object falls down, the work due to gravity is positive. If an object instead is lifted up, the work due to gravity is negative. Okay, we'll just save this in our minds. Take this information and file it away in your minds for the next few minutes, because we'll come right back to it after we do something else. Let's define an entirely new thing, something that you have not seen so far in this class, even if you have seen it in high school physics. It's called gravitational potential energy. The work done by gravity, sometimes we don't want to deal with it. So let's look at gravity through a different lens. Let's define a quantity called the gravitational potential energy. And we're going to use the letters U sub G to define that. U refers to potential energy. That means something might have the potential to do something. If I take an object and I say, well, I'm going to lift it up like that, I'm giving it the potential to do something. It has the potential to fall down. Giving it gravitational potential energy means that it has the potential to do something, and that something is fall down because of gravity. If something is not lifted up, then it doesn't have any potential to fall down. If it's on the floor or on a surface, it has no potential to fall down. If I lift it up a little, then it has the potential to fall down a little. If I lift it up a lot, then it has the potential to fall down a lot. So gravitational potential energy refers to the potential that it has to fall down, in effect. But it is a kind of energy that we're looking at. The equation for gravitational potential energy is mgy, or mgd, or mgh, or whatever other variant you've already seen of this, if you've seen a variant of this before. If you haven't, that's fine. We will be using all three of these variants because, as I've said before, every textbook is different, every class, every subject, every major is different. And so everyone is going to have different ways of expressing things. And I want you to be able to see that it's the same concept in your physics class as it is in your engineering class, for example. And so I'm going to use every kind of way of expressing this to get you used to the fact that it's all expressed differently in different subjects. And hopefully that'll help you to see the commonalities between things better. And you'll be able to take this knowledge that you've got and port it over to your other classes. Got a question, but what about positional potential? You take that car, keep it at the same height over your table. It has one energy amount. Just move it horizontally away from the table to be over the floor. Instead, it has a different energy despite not changing vertical position. Ooh, that's a good question. The question is, like, okay, if I've got it over this and it just falls a little bit, well, it's got that much potential. If I move it over here, it's got a lot more potential to fall down. The reason is you've effectively changed where the 0 point is. When it's over my hand here, then the 0 point is here because that's where it ends up going to. But when you've moved it over here, you've changed what the 0 point is to be all the way down very far on the chair. So you've just changed where you define the 0 height to be. And we will actually look at some interesting consequences of that. It's good consequences. Your question, we'll talk about it in a little bit, but your question will lead to good and convenient consequences that make our lives easier rather than harder, which I always like. Gravitational potential versus work. We see that an object, as it falls down, the gravitational potential becomes less because the equation was mgy. If you're reducing y, then ug becomes less than it was. And so delta ug is negative. If an object is lifted up, then remember the equation is mgy. M is positive, g we define as just positive 9.8. Y we're increasing, and so ug becomes more positive. And if an object falls down, then the work due to gravity, as we said several slides ago, is positive. But if an object is lifted up, the work due to gravity is negative. If you take all this and you look at the equations, you see that the way that we have defined the change in gravitational potential gets us to the point where the change in gravitational potential is equal to the negative of the work done by gravity. That's an interesting little thing right there. The change in gravitational potential is equal to the negative of the work done by gravity. We can do something very convenient with that. I said that the change in gravitational potential is equal to the negative of the work done by gravity. I also said that the work total is equal to the change in kinetic energy. But I also said that the work total is equal to the work due to gravity plus the work due to, say, springs, plus the work due to whatever else we've got, other. And that's equal to the change in kinetic energy. Let's say that we don't have any springs yet. We haven't even talked about springs. The work due to gravity is also equal, the negative of the work due to gravity is equal to the change in gravitational potential. So I can change this to negative delta UG is equal to positive work due to gravity. Just I moved around where the negative sign is. I'm going to change this work due to gravity into negative delta UG. Negative delta UG is equal to, or sorry, plus the work due to other things is equal to the change in kinetic energy. I can add delta UG to both, and I get work from other stuff is equal to the change in kinetic energy plus the change in gravitational potential energy. This might be a very familiar equation to anyone that's taken physics before, and this is how we get it. If you haven't taken physics before, then you're just learning these kinds of equations, and this will be very convenient. It'll make a lot more sense after I do some example problems with it. So don't worry too much about it right now. If you have not ever seen this before, don't worry too much. We will go over a lot of example problems where I talk about that in a whole bunch of detail.